and welcome to today's episode where I'm joined by Professor Hamkins. I don't know, are you still at Oxford at the minute? But because I know you're moving to Notre Dame or Notre Dame.
That's right. I'm at Oxford at the moment. I'm in my office here in Oxford at University College.
And in terms of how I came across your stuff, you've got a little book on proofs, which is really good. It's really helped me out a lot. And then also a book on lectures on philosophy of mathematics, which has got tons of sort of interest. Because you're a mathematician yourself, you think about things. I do philosophy, so I'm coming at things from a slightly different angle, and that has helped me to sort of see things from a mathematician's point of view as well. So if people are interested after this, those two books I would definitely recommend, and I'll put links to those things in the description. But today we're going to be talking about Frege's philosophy of mathematics. We're talking beforehand about the best way to approach this in terms of questions, and I wasn't sure if it would be useful, to kind of talk about some of the ideas that are floating around at the time. But then, that's a very broad question, as you said. Is it worth maybe just painting some of that historical background about what's going on with Frege maybe before we get into the question? So like, where is he? What kind of time period are we talking about in terms of these ideas? Just for people who are completely unfamiliar, so they've got some idea of what's going on.
Sure. So Frege was doing his work at the late 19th century, which of course was a time of enormous and extremely powerful advances in mathematics. And what had been happening at that time was a kind of systematic rigorization of many different parts of mathematics. For example, the Weierstrass epsilon delta methods in mathematical analysis gave a kind of a much more rigorous foundation to that part of mathematics. And in many other areas, there were these kind of rigorous advances and axiomatizations of different mathematical subjects. And I view Frege's work as somehow participating in that. Because he was extremely interested in providing a kind of logical foundation for mathematics and developing a kind of system in which one can view mathematics as taking place in his logical system. And so it really is a kind of participating with those logical advances in mathematics. And also, I would say that it was a time of increasing abstraction in mathematics. And of course, Frege's system is also partaking of that abstraction.
So in terms of beginning to kind of tackle Frege's philosophy of mathematics, I mean, where's the best place to start, do you think? Like, so there's broad questions which, are a part of philosophy of mathematics, like what is a number? Like what is it that we're doing when we talk about numbers and mathematics, and Frege's grappling with that. But then there's also unique parts of Frege's theory, distinctions and things. Is it best, do you think, to begin by talking about those distinctions that Frege wants to draw in his theory, or just kind of tackling head on, the big question, like what is a number, and going down that route? What would you prefer?
Oh, well, what I would prefer always is to just tackle the big question. I mean, of course, Frege's Grundlagen is remarkably readable in translation. There's some beautiful translations of it, and it's so easy to read, actually, and his writing is very clear. And so he's grappling with this big question: what is a number? And if I say there's two horses in the stable or two apples on the table, what does it mean? What is this number concept? What is the nature of these number assertions? Because the saying there's two horses in the stable doesn't seem to be a property of the horses, of either of the horses in the stable. It's and one of Frege's insights really was to recognize that those kinds of number assertions are really assertions about concepts rather than about objects. So the concept of being a horse in the stable has the property that it has two instances. And this is kind of a Fregean way of looking at what's going on. So number assertions like that are making assertions about the concepts. And one of the things that he recognized, okay, so we can kind of translate those number assertions into a kind of formal logical language to say that there are two Fs for any property F or any concept F, is just to say, look, there's an X and a Y, so that X has property F and Y has property F, and they're different. Okay, that would say there's at least two. And then we can add on the assertion. And for any z, if z has property f, then either z is equal to x or z is equal to y. And so we can kind of understand the number assertions, there are two f's, as just this kind of logical assertion in the language that's allowing you to talk about that concept f. And so that's a hint of this larger logicist program that, of course, he was advancing, which is that to reduce essentially all of mathematics to logic, maybe in a similar way. I don't know if that answers your question, but
yeah, no, I mean, it gets us started then with this big question, you know, of what is a number, and then I suppose within that, in terms of my personal studies, I guess I came across Frege's logical stuff in Begriffsschrift, concept script first. And I mean, that's kind of interesting because he does talk about concepts as, he expresses concepts, I suppose, as kind of like functions, right? So I don't know if maybe it's not helpful to mention too much about that, but I mean, where in his philosophy of maths does sort of thinking about, you know, what a function is, what a description of a thing is versus a thing that it represents, where does that fit in with his mathematical talk? Because, you know, these things called concepts seem to be doing a lot of work later on, and in terms of, I suppose, the grounding and the metaphysics of what's going on, like what are things being objects as well, seems to be relatively important to Frege. So what do these terms mean for him?
Right. So this business about this sort of concepts as functions or concepts as predications, I think is easy to go back and forth between concepts as functions and concepts as predication. If you just have the idea that, look, if I have a predicate, I mean, maybe I should start like this. So Frege's ontology makes a clear distinction between objects and concepts. So the way I think about it is, the objects are this sort of realm of individuals, of individual objects, and when we make quantifier assertions, we can quantify over all the individuals, and they might have various properties. But concepts are kind of predicates on top of that realm of individuals. So we can say that a particular individual falls under a concept or is predicated by that concept if it has the property that concept is expressing. If it's a horse in the stable, then that particular horse in the stable will have the property of being a horse in that particular stable. And so for Frege, a concept is kind of a predicate or a class of individuals. And so it aligns very closely with the way we think in contemporary mathematics and logic about sort of the first order, second order distinction. So first order objects, we have a realm of individuals, and second order objects are sort of classes of individuals or predicates. And so, and then the difference between a predicate and thinking of a predicate as a class of individuals or as a function that maps the individuals to the true or the false is almost inconsequential. We can easily translate between that. It's the difference between having a set or having the characteristic function of a set. So the characteristic function of a set is the function that maps every possible individual to either 0 or 1, depending on whether it's in the set or out of the set. And so usually value 1 means it's a member of the set, and value 0 means it's out of the set. And so Frege is thinking about the concepts in this kind of characteristic function manner, but we can easily translate back and forth between those. I mean, one of the things about this sort of number, what is a number question, is that Frege emphasized this. What was very important about that kind of number talk was that the distinctness and individuation of the individuals for which we're making the number assertion. So when I say there's 2 horses in the stable, then we have to be able to distinguish the horses as particular individuals, and that would fit in with his ontology. It's a very different kind of assertion than to say that there's 10 gallons of gasoline in the tank. Because when I say there's 10 gallons of gasoline in the tank, then I'm not talking about 10 individual gallons. I mean, if I had a tank of gas and it had 10 gallons of gasoline in it, then I'm not counting them 1, 2, 3, up to 10. And I mean, actually, if I think about sort of individual collections of molecules of gas in the tank, there's way more than 10. Even in a 10-gallon tank, there's probably hundreds of millions, depending on exactly how I count those guns, at the one on the bottom and the one on the top and on the left and the north side and so on. There's one exactly in the middle and then 1 millimeter to the left. If I think of all those different ways I could chop up that volume of gasoline into a 1 gallon unit, there's way more than 10 in a 10 gallon tank, right? And so we lack that kind of individuation. So Ian Rumfitt emphasized another kind of problematic thing for the way that Frege sometimes talks about numbers. Like, consider the statement, at least 3 engineers are required to operate the train safely. But if you need at least 3, then you also need at least 2, right? And so it would seem logical that you should be able to truthfully say at least 2 engineers are required to operate the train safely. But that seems wrong, because if you need 3, then it's wrong to say that at least 2 suffice if you're somehow saying that 2 would suffice. Or if I say the concert hall seats at most 800 people, well, 800 is less than 2,000. And so is it also correct to say that the concert hall seats at most 2,000 people? I think many people would object to that statement if 800 was the actual maximum number. So you can find some instances of number talk in the style that Frege was mentioning that don't quite fit in with his framework. But okay, so he's talking about these other kind of clear-cut cases when we're talking about individuation and able to distinguish the individuals. So we have this kind of realm of individuals and properties or concepts on those realms, and we want to be able to make number assertions about how many instantiations of a given concept there are.
So broadly, I suppose, on our way to talking about this big project of logicism for Frege, we're going to have to introduce maybe a few, well, there's a few kind of stops along the way. So one of them might be extensionality, which might be a word that people haven't come across before. So would you be able to sort of clarify what is extensionality for Frege? And then maybe, why is that relevant to something called the Cantor-Hume principle, which you talk about in your book a little bit?
Right. So Frege had this idea of extensions of a concept. And actually, that word has a very different connotation today than it had in Frege's work, I think. So now when we talk about the extension of a concept, there's a connotation that we're talking about a collection of some kind. The extension of a concept is almost, in today's language, it means the set of instances for which that concept holds. But that's not how Frege thought about it. The extension of a concept was very much connected with his basic law 5, which I think we'll get into later. And the extension of a concept was sort of an object that represented the concept. So he had these concepts, which are these kind of second order, what we would now call second order objects, predicates on the first order realm of individuals. But he wanted to think about those concepts as objects themselves. And so he had this extension idea. The extension of a concept is an object, thinking of the concept as an object. But it led him into trouble, actually. When he wanted to think of concepts as objects, then he got into trouble, which Russell eventually pointed out to him, and it ultimately made his system inconsistent. This idea of wanting to represent every concept by an object, the extension of that concept.
So how is this relevant then to the Cantor-Hume principle, which you talked about in your book? And firstly, I mean, what is the principle?
Sure.
And
yeah, so the Cantor-Hume principle, it's also called the Hume's principle. Many people could just call it Hume's principle, but I prefer to call it the Cantor-Hume principle because of Cantor's use of it in such a dramatic way. So earlier than Frege, and Hume mentioned something very specific. So let me just say what it is. The Cantor-Hume principle is the assertion that the number of F's is the same as the number of G's, just in case F and G are equinumerous, just in case we can put those concepts into one-to-one correspondence with each other. So 2 concepts or sets or classes, however you want to talk about them, are equinumerous if there's a one-to-one association between the instances of the first class with the instances of the second class. So it's maybe easy to give an example. If I'm looking at a dining table set for dinner, for a dinner party, I might be able to observe easily that the number of plates is the same as the number of forks, because I can see at each place setting there's 1 plate and 1 fork. And so I have a kind of one-to-one correspondence between plates on the table and forks on the table. And so I know that the number of plates is equal to the number of forks. Even if I haven't counted them, I might be able to tell that those numbers are the same. So that's an instance of the Cantor-Hume principle. It says the number of f's is equal to the number of g's, just in case f and g are equinumerous. And Hume says something very much like this in his writings. He has a few sentences where he expresses this idea, and Frege had mentioned that, and so this is why it came to be known as Hume's principle. But Cantor, of course, also used this principle in his theory of cardinality, particularly in the case of infinite sets, quite dramatically, showing that the reals are uncountable and that there are even larger uncountable infinities. And so Cantor took this principle basically as the basis of his theory of cardinality, making all those dramatic conclusions, especially for infinite sets. Frege was much more focused on the finite cardinalities, and in particular arithmetic. In his logicist program, he really wanted to give an account of arithmetic, meaning for finite numbers, for the natural numbers. And so he wasn't so much concerned with Cantor's aspect or Cantor's use of the Cantor-Hume principle. Actually, it might be interesting to point out that Galileo used something very much like the principle before Hume even. So Galileo had pointed out, he was very confused about the fact that the number of positive integers can be put into one-to-one correspondence with the squares, because I can associate every number with its square, 1 with 1 and 2 with 4 and 3 with 9 and 4 with 16 and so on. And so I seem to have a one-to-one correspondence between the positive integers and the perfect squares. And this was confusing to Galileo, or to Galileo's character in the Two New Sciences dialogue, really wonderful dialogue, exploring these issues. And so Galileo came to the conclusion, look, it's not sensible to make size comparisons between infinite sets, or to say that one infinite set is the same size as another or bigger. So he's, in a sense, considering the Cantor-Hume principle, but rejecting it ultimately as nonsensical, because it would force him to give up the Euclid's principle that the whole is greater than the part. Namely, the set of all the positive integers seems to be bigger, strictly bigger than the set of perfect squares. And so Galileo didn't want to accept the idea that the number of squares would be the same as the number of natural numbers.
It's very interesting, as you explain that, to sort of think about the different way that people historically have thought about some of these concepts as well. Because obviously someone such as myself approaches this from an angle where there's just so many textbooks and stuff about maths, so you can approach this, and there's well-defined kind of different areas of mathematics already established. And it's interesting, when people are far more influenced by Euclid, for example, and like a principle like that, to see how they'd think about it. Whereas for me, something like that, I've not had such certainties when it's come to like figuring out what mathematics is, what it does, and things that have influenced me. Anyway, in terms of, would it be good then at this point do you want to go through logicism to the Julius Caesar problem, or the Julius Caesar problem?
Yeah, let's just talk about Julius Caesar. It's a really wonderful kind of issue that Frege had identified with the Cantor-Hume principle. So he was interested in the question of what is a number, and he had an account of what it means to make specific number assertions in terms of these logical expressions, and he identified the Cantor-Hume principle as sort of a fundamental feature of what it would mean, what a kind of equivalence that numbers should obey, namely that the number of f's is equal to the number of g's if and only if f and g are equinumerous. But he recognized that the Cantor-Hume principle doesn't actually tell us what numbers are. It only is a property that they would have to obey. And maybe one way of thinking about this property is that it's saying, if we think about concepts under the equinumerosity equivalence relation, then the Cantor-Hume principle is saying that we're assigning to every concept this number, and it's what's called a classification invariant for equinumerosity, meaning that whenever two concepts are equivalent, then they get the same number. And whenever two concepts are inequivalent, they should get different numbers. And so it tells you when numbers are equal to each other, but it doesn't tell you, for example, whether this pen is a number, or in particular, whether Julius Caesar is a number. I mean, it's kind of absurd to talk about the question of whether Julius Caesar is a number, and maybe one has the sense that Frege thought that Julius Caesar should not be a number. And I think this is a kind of presumption that many people have, that, well, of course, Julius Caesar isn't a number, and the spoon on the table isn't a number either. But this is exactly what goes strongly against the philosophy of structuralism, actually. It reveals that the worry about the Julius Caesar problem is an extremely anti-structuralist worry, because according to the philosophy of structuralism, then we really only care about mathematical objects or mathematical we only care about our mathematical assertions up to isomorphism. So if I have one system of numbers or another system of numbers and they're isomorphic, then they're equally good and have an equal claim to being the status of a number. And the structuralist philosophy is that it's misguided and mathematically unenlightening to ever inquire about the sort of fundamental nature of what a mathematical object is, precisely because we can take any mathematical object and have an isomorphic copy of it, and that other copy is just as good, fully just as good for any mathematical purpose as the original one. This philosophy is pervasive today in mathematics. And the Julius Caesar problem is anti-structuralist, because it's asking whether Julius Caesar is a number or not, or worried about the question of how can we tell whether or not Julius Caesar is a number. But the structuralist attitude would be to say, it doesn't matter if Julius Caesar is a number or not. And if he's not a number, then I can make another number system in which he is the number, because you can just take any copy, say, of the integers. And if Julius Caesar isn't a number in that copy, then I can take the number 7, for example, and remove it from the set, whatever it was, whatever object it was that was represented the number 7 before, and I can put Julius Caesar into that slot, and now I've got a new number system in which Julius Caesar is a number. He would be the number 7 in that system, and I could make him any number I want, and it would be just as good a mathematical structure as the original one, because it's isomorphic. And so therefore, on this kind of way of thinking, on this structuralist view, the Julius Caesar problem is seen to be anti-structuralist.
So Frege, he doesn't sort of resolve this. He sort of raises the question, right? But he doesn't resolve it either way in his thought. So.
That's right. So ultimately, of course, he's going to justify the Cantor-Hume principle on the grounds of his basic law 5, and it's the number of a concept will be the extension of the concept of being equinumerous with that concept. So should we get into that a little bit, or what do you?
Yeah, we can. I was wondering, maybe just before that, are there, do you know anything about like what kind of considerations are driving Frege in the first place to sort of think that everything would be reducible to logic in some sense, that logic is more fundamental, and that he'd be able to engage in such a program, as opposed to taking, I don't know, arithmetic itself as like the basic thing instead. Well, like platonic forms of the numbers or something. Like, why does he think that discourse is going to be eliminated into logic?
Right. So, I mean, ultimately, he was successful in giving a definition of number that did fulfill the Cantor-Hume principle, because, it's a fundamental idea that he had, which is now pervasive in mathematics, and it's known as the quotient construction. I mean, in every subject of mathematics, they're doing exactly the same kind of construction. Namely, whenever you have an equivalence relation, so a notion of objects being equivalent, then you can always consider the equivalence class of an object, which is the set of all the objects equivalent to it, or the concept of being equivalent to that object. And the point is that the equivalence class of an object is always an invariant with respect to that equivalence relation. And so what this leads Frege to say, well, look, what a number is the extension of the concept of being equinumerous with that concept. So So the number 2 is in a sense, the concept of having 2 elements. Okay, so this is the equivalence class of all the 2 element sets, if you want to think about it that way. And the number 3 is the class of all 3 element sets. And the number 0 is the number of any property that doesn't have any elements, or the number of a contradictory property, if you want. And so one can show, I mean, it's a theorem basically, that if you define numbers that way, then you're going to fulfill the Cantor-Hume principle. And so in this sense, it does provide a reduction of mathematics to logic, I think, as far as that is concerned. Now, Frege used the basic law 5 in order to undertake that argument, because he's defining the number as the extension of a certain concept, and basic law 5 is what entitles him to know that every concept does have such an extension. I mean, it's an instance of what might be called Fregean abstraction. So Fregean abstraction is whenever you have a notion of equivalence, then you have the abstraction of that equivalence. So if you know, for example, if you have a concept of parallelism for lines are parallel, it's an equivalence relation for lines, and then you're entitled to refer to the direction of the line. What is the direction of a line? Well, it's the invariant it's the we can assign to each equivalence class of lines this thing called the direction of the line by an instance of Fregean abstraction, in the same way that we assign the number object to any class with respect to the equivalence relation of equinumerosity.
So in terms of maybe if we go through logicism first before coming on to paradoxes and stuff that sort of fall out of basic law 5. So what are the primary what other considerations then are there in sort of Frege's attempt at reduction? So there's this idea maybe that you can construct a class for any kind of definable thing or something like that. Is that one of them? So yes.
So Fregean abstraction is the idea that for any notion of equivalence, we can assign the abstraction of that concept and get these kind of objects. That's what numbers are. That's what directions are. That's what extensions of concepts are. They're all instances of Fregean abstraction. So using that idea, Frege established the Cantor-Hume principle, and then he argued on the basis solely of the Cantor-Hume principle that his definition of numbers fulfill the dedekind arithmetic axioms, the idea including second order induction and so on. So Frege's theorem is the idea, is the statement that using the Cantor-Hume principle as established by basic law 5, we get the dedekind axioms of arithmetic. And Peano had proven quite elegantly and remarkably from the dedekind axiomatization, which is also now often called the Peano axiomatization, developed essentially all of the fundamental truths of arithmetic on the basis of those axioms. So once you have the dedekind axioms, which is the assertion that you have numbers, including the number 0, and you have the successor operation, which is 1-to-1, and you have this induction axiom, then on the basis of those 3 principles, you can define addition and multiplication and exponentiation, and you can prove all the fundamental facts, commutativity and associativity and distributivity and all the familiar arithmetic facts, and you can develop the theory of prime numbers and so on. All of it is just coming directly out of those axioms, as Peano showed so elegantly. And Frege, in establishing that dedekind arithmetic axioms hold for his concept of number, is entitled to all of those conclusions on the basis of his purely logical definition.
Without, obviously without notation stuff, because we're sort of verbally communicating, would it be too difficult, do you think, to talk a little bit about, how Frege goes about defining something like the successor, because it's like, well, sure, okay, we can get 0 by saying that's, the empty set or whatever. And then how does Frege go about, defining, firstly, how does he go about saying there's only one successor of each thing, I suppose, and then say, showing that there is a successor in logic?
Right. So he talks actually, I mean, it's a bit anachronistic. So he talks about the predecessor relation. It's the more fundamental thing for him. And he says, so X is a predecessor of Y exactly if X is the number of the concept that you would get by taking any concept that's represented by Y and removing one element. So basically he's saying, look, the predecessor is the number that you get if you take one element out. So if you have a certain number Y of horses in the stable, then X is the predecessor of that if you fix any particular horse in the stable and then look at the concept of being all a horse in the stable except for that one, one less, basically. So that's how he defines predecessor. And then he has this idea of the ancestral relation. And so, but of course, once you have the predecessor, you can define successor kind of as the inverse. And so this is a kind of deDyschen manner of talking about it in terms of successor instead of predecessor. And then ultimately, a natural number is something that has every property that zero has and which is always passed from an object to its successor, which is a kind of inductive way. I mean, it amounts to showing that the natural numbers are what you get if you start with zero and then you apply successors and keep closing under that. So the natural numbers are the closure of zero under the successor operation is what it amounts to. But that's how he explains it in terms of these ancestrals of the predecessor relation.
Now, is it worth talking about neologicism before or after the sort of Russell's paradox that comes up?
Right. So I guess I've already basically explained the main idea of the neologist is to point out, although Frege had used basic law 5 to establish the Cantor-Hume principle and then proved the deDyschen axioms on the basis of that, the only problematic part of his system was coming from this basic law 5 part, as Russell pointed out, which I'm sure we'll get to. But the rest of the argument is totally fine. And the Cantor-Hume principle is completely accepted in contemporary mathematics, and one can still use Frege's argument to show that it leads to a number system fulfilling deDyschen's axioms. So that's the main neologicist observation, is that Frege, in fact, had succeeded in that other part, and Russell's argument doesn't get rid of all of that part.
So then in terms of the problem with basic law 5, so we sort of talked about a similar problem, I suppose, already when said, for Frege, concepts aren't objects, but you can sort of, you can sort of refer to concepts as objects. So that sort of creates this problem, which I'm more familiar with from, which is there in his philosophy of language as well. And then there's this sort of self-referential problem that comes about that Russell points out. So what is the problem, I suppose? What is it that Russell notices, and what's the historical story as well about what happens here?
Right. So the story that one can tell, I think, in the most successful manner is to say that Russell refuted what's known as the general comprehension principle. The general comprehension principle says, look, if you have any property at all, then you can form the set of all X of things that have that property. And it sounds quite reasonable at first. Maybe if you have a kind of naive picture of how set theory works, then yeah, if you have a property, you should be able to take the set of all things that have that property. That should be a set. And Russell pointed out that actually this is wrong. It's very easily refuted, because look, we could form the set of all sets X so that X is not a member of X. X not being a member of X is a perfectly ordinary property. Most sets have that property, because, for example, the set of all elephants is not an elephant. It's a set, and it's not an elephant. So the set of all elephants is not self-membered, and the set of objects on my table is not self-membered, because that isn't an object on my table. So it's a perfectly kind of ordinary property that Russell is considering. And he's saying, well, let's take the set of all non-self-membered sets, X. And the difficulty now is that if that's a set, which it would be under the general comprehension axiom, then it would be an element of itself if and only if it wasn't. because the only way to become a member of that set is to not be a member of yourself. So if it wasn't a member of itself, it should be, and if it was, it shouldn't be. And that's a contradiction. So Russell is refuting the general comprehension principle. This is a kind of usual way of explaining the Russell's theorem. But, okay, the difficulty for Frege is that he didn't actually state the general comprehension principle as one of his fundamental axioms. And so both Russell and Frege laid the blame at basic law 5 in their letters to each other and in his appendix where he's explaining that his system is refuted. He said the problem is basic law 5. And basic law 5 is the assertion that he has this idea of this assigning extensions to concepts. And it's the axiom that says the extension of f is equal to the extension of g if and only if f and g have all the same instances. So for all x, fx if and only if gx. And so, but that doesn't sound anything like general comprehension. And it's not the general comprehension principle. Rather, the general comprehension principle is baked into Frege's system because of a kind of notational matter. He can form the terms for those sets. And he can just make the term which would stand for the extension of the concept of f is basically the set of all x with property f. That's what it amounts to for Frege's system. And so I view it really as Russell's argument is refuting general comprehension. And the point is that the basic law 5 is what you need in order to know that the element of relation is working as you expect it to work for classes. So it's a combination of his implicit commitment to the general comprehension principle plus basic law 5 that's really being refuted by Russell. There's a couple of sort of a more colloquial way to describe the Russell paradox. I mean, it's often described with the Barber paradox. So should we talk about some of those?
Yeah, we can do. People as well who might be interested in this. I had Graham Priest on yesterday as well, talking about dialetheism. So there's a general theme here that's coming out of our weird logical puzzles. But yeah, let's absolutely talk about Russell's paradox, which is more colloquially mentioned.
Sure, I like Graham a lot. He was a colleague of mine when I was in New York. Before I came to Oxford, I was at the City University of New York, which is where Graham Priest is now. So I know him well. So the Barber paradox is the paradox of the barber in town who shaves all and only those people who don't shave themselves. And the logic of it is very much like the Russell paradox, because you can ask, does the barber shave himself or not? Well, he shaves all and only those who don't shave themselves. So if he does shave himself, then he shouldn't. And if he doesn't, then he should. It's exactly the same logic as the Russell paradox. Also, there's my wife, Barbara Gail Montero, talks about the barista who serves coffee to all and only those who don't make coffee for themselves. And of course, this is the same logic again. So there's an extreme similarity between the Russell paradox, which Russell mentions, and Cantor's proof that every set has more subsets than elements, strictly more. So in other words, Cantor proof, this is way before, well before Frege and before the Russell paradox. Cantor proved that you can never have a one-to-one correspondence between the elements of a set and the subsets of the set. And the way to prove that is, well, if you had such a correspondence, then you should form the set of individuals from the set that are not in the set that corresponds to them. And so that would be a subset, maybe empty, maybe everything, maybe just some of them, whatever it is, but it couldn't be associated with any individual because that individual would be in that set if and only if it wasn't. And so that's Cantor's argument, decades before Russell. And Russell says, look, the logic of his argument is basically the same as Cantor. And it shows you what's wrong with Frege's idea, that he had the realm of objects and he had the predicates on top, the concepts. Those are like all the subsets. And Cantor says, look, you always have more, strictly more subsets than objects. So you can't assign to every concept an extension object in a one-to-one way. which is what basic law 5 is asserting. And so that's why I see a very tight connection between Cantor's theorem on the power set, which is, of course, a generalization of his theorem that the real numbers are uncountable. There's a very tight connection between Cantor's theorem and Russell's refutation of Frege's system.
So how is it that sort of Frege takes this news, as he gets this letter from Russell, and my understanding is that he's got a second edition of the Grundlagen on the printing press or something, and he sort of runs off to stop this, but stop it printing out. It's sort of held up as a paragon of someone changing their mind actually and accepting the kind of refutation and acting quite admirably in a way. But how does Frege then sort of respond? What's his attempted solution, and is it successful?
Right. Well, he was extremely gracious in his reception of Russell's argument. I mean, it was, of course, devastating for his system because it showed his system was inconsistent in a fundamental way. It wasn't just some detail, but really the way he was using basic law 5 and his term algebra was completely refuted by Russell's argument. And he was so gracious in his appendix. He had this remark, and there's this famous quotation about there can hardly be anything more disheartening to just as the edifice is completed to see the foundations be shaken. And so in a sense that, I mean, he couldn't continue with that axiomatization, and he did more work after that. But basically, the original Frege term logic, as it was conceived in that work, was irreparably damaged.
And then I suppose a last kind of question from me, and then we'll go over to some questions from the chat. So if people have got them and they want to tag me, just put them up and I can bring them up in a moment. Would be, how has this affected sort of subsequent attempts to reduce mathematics to logic? So sort of in that, I'm familiar with obviously Russell and Whitehead's work, familiar with like Russell's type theory, or Alonzo Church's sort of a type theory stuff as well, though I'm not an expert on any of these things. So how is it received, and how has it affected the subsequent sort of series of attempts to reduce mathematics in this way? Oh, and I think von Neumann tried to do something. Did he show that it's indeterminate which way you look at it or something? Yeah, I'll hand it over to you and you can.
Right. So there's huge amount of work coming after that in the foundations of mathematics, and a huge amount of ink spilled in philosophical analysis of logicism. I mean, there's one way of looking at it as a question of terminology. I mean, a lot of these arguments turn into a discussion of, well, what counts as logic? For example, Zermelo proposed his axioms shortly after that time, and Zermelo's set theory became a very prominent foundation of mathematics, in which one can view essentially all of mathematics as taking place in set theory on the basis of the Zermelo-Fraenkel axioms. And if one were to regard the axioms of set theory as fundamentally logical in character, which I do actually, then this is a complete success for logicism. So the set theoretic foundations of mathematics is implementing mathematics on the basis of fundamentally logical principles of set theory. And I think that's a perfectly legitimate way of looking at logicism as completely successful. Okay, not everyone agrees with that perspective at all, because they say, well, things like the axiom of infinity and the axiom of choice are not fundamentally logical in character. And so this is what I meant by the debate turning into a question of, well, what counts as logic? Is second order logic? Is that logic? I mean, Quine famously said this is set theory in sheep's clothing. And so if one doesn't count second order logic, Frege's system was second order in nature fundamentally. And inherently, actually, if you just take the first order fragment of Frege's system, it's not inconsistent, and Russell's argument doesn't work. So the basic law 5 considered as a first order system is consistent. And so he really was using second order logic, but many people have argued that second order logic is really just set theory. And if you have the view that set theory doesn't count as logic, then maybe you should have the view that second order logic is not really logic, but mathematics, because it's set theory. And so, I mean, I wouldn't want to say, I mean, the idea that somehow the whole debate is a kind of terminological dispute is not really correct, because of course we have the idea that to judge something being a successful instance of logicism would mean that we are able to implement mathematical foundations using purely logical ideas, meaning not just that we're going to call it logic, but that it's obeying the fundamental principles of what logic should mean, and have the right sort of necessity claims being made about it, and so on.
Awesome. I'm just looking through the chat because there's quite a few people have been putting questions throughout. So
okay, great.
Thanks for that. So one question here was, yeah, are you? I think Susan Bobzian, who I think might be at Oxford, has done some work recently. I think it was last year or this year, saying that Frege plagiarized the Stoics. I don't know. Are you familiar with?
I don't have anything to say about that. I'm sorry.
Okay.
I don't know.
And then a second question from the same person was, presumably C.S. Peirce's thinking on existential graphs had not been published early enough to have any possible influence on Frege's graphs,
right.
But similar.
So I'm sorry.
Yeah, I think this is in terms
I don't know
of.
the answer. I mean, in a sense, I come from set theory, and I'm looking at Frege from this sort of set theoretic perspective, and interested in Russell and so on. And I'm not really familiar so much with the with that part of the Frege scholarship.
So another question from a different person, Roman, asks, how much does Platonism influence Frege's project and its later downfall, especially in regard to basic law 5 and Russell's paradox? Can Hume's principle still be used like neo-logicists propose? I suppose we slightly touched on that. But. Right.
So we touched on it a little bit. So the neo-logicists, I think, are really emphasizing the idea that from Hume's principle, or what I call the counter-Hume principle, one can get all of arithmetic. And I think that for Frege, it is a form of Platonism, and so he's using those principles really with a Platonist perspective. You know, he has this realm of objects, and the concepts on it, and he's thinking of all these abstractions as fully real objects, which is, of course, a kind of Platonism.
Is it right to sort of think of it that you know, it's not so much that the numbers themselves are sort of these Platonic forms, but it is right that there's sort of Platonic forms, as it were, that are playing roles in the theory. So, like, you know, the true and the false, and maybe various like logical apparatus that construct.
Well, it's not just that, but the Hume's principle itself is it's important for Hume's principle that the numbers of the concepts be objects themselves, right? And this is related to the extension of a concept that, you know, the idea mentioned in Basic Law 5, but they're both Fregean abstraction principles, and it's important, I think, in both cases that the abstraction objects are objects in the realm of objects. I mean, it's interesting when you think about the Julius Caesar problem. Frege considered it in connection with the Hume principle, but he didn't seem to consider it so much in connection just with Basic Law 5 itself. But it's exactly the same problem as far as I can see. If we're worried about whether Julius Caesar is a number, why aren't we worried about whether Julius Caesar is the extension of the concept of being a horse in the stable, or any concept? So is Julius Caesar the extension of a concept? I mean, maybe you think, well, obviously not. But why should you think that? Because there's no axioms in Basic Law 5 that would seem to determine whether something is or is not an extension, which just saying two extensions of concepts are equal if and only if those concepts have the same instances. So it seems exactly analogous, the Julius Caesar problem. And I find that quite interesting. And it's connected with this Platonism issue, because if we think of the extension of a concept or the number of a concept or any of these instances of Fregean abstractions as the objects, then this is a kind of Platonism about those abstractions. And so it's going to be subject to the Julius Caesar problem.
Awesome. So let's see. Why does predicate precede subject in notation, even though subject precedes predicate in speech, merely because copying over function notation from maths? ?
Oh, I see. Well, that's quite interesting. I mean, it's a notational matter. Of course, what a mathematician would say, well, look, it doesn't matter if you write it before or after. I mean, that's just a notational distinction. And we have lots of different notations in mathematics, including in logic. And Frege famously, starting in the begriffsship, had his kind of logical notation that he set up. And some of those ideas were carried further, but a lot of his notation, thankfully, was abandoned and simplified by in current usage. Although conceptually, it's very similar. And so we can view, say, the main concepts that are used in first order logic really grow out of Frege's work, but his notation is often not. But some of it does survive. And so, of course, we can have prefix, postfix notation, whatever you want, and somehow translating between these. And so what does it matter whether we put it first or second? Maybe the linguists would have stronger views on that. But in terms of logic and mathematics, it just doesn't matter, it seems.
There's a question that sort of spans over two. So the first part of the question is, in your books, you present mathematical proofs of quite different kinds. Historically, a proof consisting of steps logic has long been... Oh, I think, and then it sort of like shifts a bit. Books present mathematical proofs of quite different kinds. Historically, a sequence of inference has long been regarded as proper proof. Does Frege's logicism allow for wider notation of proofs?
Right. So Frege developed his formal system for giving formal proofs, and that's extremely important. That was an extremely important development for the rise of proof theory. And of course, today we have many different formal proof systems. And I view those all as somehow growing out of Frege's work. If you're referring in my Proof in the Art of Mathematics book, where which is a book I wrote for helping to teach aspiring young mathematicians how to write proofs, then it has nothing whatsoever to do with a sort of formal proof, but rather just understanding the nature of making a sound logical argument. And it's, I think, to my way of thinking, important to keep in mind the distinction between having a formal proof in the sense of having a proof that obeys the rules of a formal proof system, and having a proof of a mathematical theorem. If you go back and look at Euclid's book, Euclid's Elements, there's nothing like a formal proof system in that book, and yet it's the paragon of formal mathematical argument, deductive reasoning. Euclid's proofs read like prose, and they're not formal in any sense. They consist of sentences with sort of ordinary language use and periods at the end and so on, and quite readable, completely contemporary. I mean, it's like the proofs that you find in a contemporary mathematics journal or in a lecture hall. If a mathematician is giving a proof of a theorem, they're generally not using those formal proof systems. So the way I view it is, Frege is trying to introduce a kind of foundational ideas about what it really means ultimately to have a formal proof, and the rest of mathematics is proceeding on this comparatively informal manner, and I wouldn't want to see that informal kind of proof abandoned or neglected, because when we understand a theorem, we understand the theorem on the basis of those more informal arguments that express the true content of the mathematical ideas rather than a formal proof. For example, Bill Thurston really emphasized this point, the distinction between having a formal proof and having some understanding of a theorem. And of course, we always want the understanding in favor of checking the details of a formal proof, unless the idea is in doubt or something. Of course, if we have doubt about the informal argument, then it's nice to have the formal proof, because maybe that helps us to feel that we didn't make a mistake in it. But in very few instances are we getting the kind of mathematical understanding and insight from a formal proof that we would ordinarily get from the informal proof.
So another question then was, have you got any books on the books at the minute, as it were?
I have about 5 books I'm writing at the moment, but I think the next one that will be finished is called Topics in Logic, and it's a kind of sweeping account of the enormous breadth of the subject of logic, including propositional logic and predicate logic and logic of games and the relational logic and model theory and epistemic logic and modal logic. And what I want to do is somehow broaden the scope of what's normally studied by students of logic when they first see logic, rather than concentrating on a relatively narrow selection of topics from logic. I want to show them the enormous scope of the subject of logic. And so that's Topics in Logic. It'll probably be out in a year or two.
That's really interesting, because my undergraduate degree is in software engineering, and I'm doing a master's now in philosophy, and I worked as a software engineer for a while. But coming across the use of logic as it's implemented almost in programming languages, versus then coming across it as, I suppose, in philosophy as a quasi-historical, but also you're practically using it to argue as well. And there's this chasm in the thinking between the two kind of subjects in the way.
But it's not it's completely filled in, because there's all kinds of other topics that fill in intermediate places between those and extending on either side beyond. I think logic is just an enormous subject and has so much fascinating work and so many interesting ideas. I want to just share it with everybody.
So a question here then is, does the HPE, presumably Hume principle, versus the EM, I'm not sure what that one is, but hopefully you do, resolve concepts such as actual infinities? Seems if A and B are allowed to be sets that have infinitely many elements, both cannot be correct.
So what is EM? I'm not quite sure what.
Yeah, I'm not quite sure. I'm just looking through the chat to see if I can see it put anywhere. Maybe if you're still here, Doc Pleromenaut, put what EM is and we could come back to it. Okay.
Maybe he means the Euclid's principle, maybe. So I mentioned this tension between the Hume's principle and Euclid's principle. And so this is brought out by Galileo also. I mean, and his example with the perfect squares is already an instance of this kind of conflict, right? And Galileo also pointed out, look, if you have a line segment, a short one and a long one, then you can imagine a one-to-one correspondence, this sort of draw a fanning of lines between them, and it would give you a one-to-one correspondence between a short line segment and a long one. And he also describes how to make a line segment equinumerous with the entire number line, with the entire real line. And so this is another instance where his characters sort of throw up their hands and say, therefore, we don't understand infinity. But I think the right way to understand Euclid's principle is by replacing it with a reflexive version, namely that the whole is at least as big as any proper part. And then everything's fine. That's totally compatible with Hume's principle. So, in fact, it gets into this. There's something missing from Frege and the logicist analysis of Hume's principle, or the counter-Hume principle, in that it gives the criteria for equivalence of numbers, but he doesn't have any criteria for comparison of numbers. And so it seems like it would be very reasonable for Frege. He could have said that one number is less than or equal to another number if the first concept is equinumerous with a subclass or subconcept of the other one. So that would correspond to having a sort of injective map from the first class into the second one. But then the question would arise, well, look, if the number of f's is at most the number of g's, and the number of g's is at most the number of f's, does that mean that those two numbers are the same? And maybe you think, well, that's obvious, because of course, if x is less or equal to y and y is less or equal to x, then x should be equal to y. But you don't want to assume that. We want to prove it, basically, that it would be true of Frege's number concept. And in fact, in set theory, this is a theorem known as the Cantor-Schroeder-Bernstein theorem. And it's not trivial. It's not a trivial theorem. In fact, it confused those people. And that's why it has 3 names, because it came in various proofs, and the proofs were shown to be wrong, or that they used the axiom of choice, but they didn't need to, and so on. And so finally, it now has established proof. The Cantor-Schroeder-Bernstein theorem is the principle of antisymmetry for Frege's numbers, basically. And to my way of thinking, this is just as important a principle as Hume's principle is. And whenever one states Hume's principle, then the very next thing you should say should be a statement of the Cantor-Schroeder-Bernstein theorem, namely that if the number of f's is less or equal to the number of g's, and the number of g's is less or equal to the number of f's, then those 2 numbers are equal. And that's true for infinite sets, finite sets, all sets in a very general way, because of the Cantor-Schroeder-Bernstein theorem. So it's related to this reflexive version of Euclid's principle, which kind of solves the tension between Hume's principle and Euclid's principle.
So just a couple more questions then. One of them should hopefully just be clarifying something for someone, where they said, what is the metaphysical status of mathematics according to Frege? So is it a form of idealism, a variation of Platonism? We kind of have touched on that, but just to maybe clarify it in the terms of the questioner here, maybe.
So, well, I don't want to speak for Frege, but I mean, I think Frege ultimately in the Logicism program was attempting to reduce mathematics to logic. And so I think he thought of those logical concepts and the objects as real. And so that would be a variation of Platonism, I guess. And the instantiation of extensions of concepts as objects is, I guess, not really a form of idealism, but rather the opposite. So, but one should really ask Frege himself.
Sorry, I was just getting the link from your website as well to put it in the chat for people,
Okay,
so they can go there. So the last question someone has asked, can you suggest some good books to start with logicism and related topics?
Well, I would start with the Grundlagen, because, as I said early on in the interview, it's very readable in translation, and so you can just start immediately engaging with the question of Frege's program, his logicism program, and he's talking there about what is a number, and giving the ancestral arguments and so on. All of it is right there, and it's very readable.
Awesome. Well, I've put the link in the chat so people who are watching live can click on that if they want to check out more of your stuff, and I'll put the links in the description if people are watching later. So yeah, thank you for coming on. I put a random tweet out a couple of months ago seeing if someone was willing to come on and talk about the Frege's philosophy of mathematics. So thanks for sort of taking the gauntlet there and stepping up to the plate for a random kind of tweet as well.
Well, thank you very much. It was a pleasure to be here and talk with you about Frege. Thank you.
Great. So I'll just play the end credits, and then if you want to hang around for a moment, you can, and I'll just say bye. But other than that, thank you everyone for watching. There's a couple more discussions on the channel over the next couple of weeks that people might be interested in. Namely, Graham Oppie is going to be talking to Bernardo Kastrup about whether physicalism or idealism is true. So those are 2 people that I think a lot of people in this space are quite interested in, and they're coming together to dialogue here. So be sure to set a reminder for that if you are interested in that kind of thing. Other than that, thanks everyone, and I'll see you next time.